Thank you very much. It's a great pleasure to be here. Hopefully everybody can hear me. Um, I will be talking today a little update on what's up with chalcopyrite solar cells, although I have to admit that kesterites will show up a little bit. And lest you wonder whether Cigs arrays exist, I'll show you a picture here on the first slide of my 4.5 kilowatt Solibro Cigs array in central Illinois, which is working very nicely. So I didn't know exactly who would be attending this. I thought it might be a good idea to start with a little bit of an introduction to the device, a little sort of general background to make sure we're all on the same page, look at the substrate and interconnect methods that are used with this technology, review the materials we're talking about briefly and the methods for making them, and then we'll talk about the products and production processes that are in use and the technical and scientific questions, at least a couple of the technical and scientific challenges that remain for the technology. And I'll be happy to take questions at the end. And I'm not going to cover all of the technical challenges. I'll just cover what I perceive as a couple of the major ones. As an illustration, if you have something on your mind, hopefully you can ask about that. I can't see questions that are typed into the chat line, so if there are questions on the chat line, I hope somebody will read them to me. So let's look at the device to begin with. It is a so-called substrate geometry device, usually made on soda lime glass or a couple of other materials we'll talk about in a couple of minutes. The back contact is generally molybdenum. It's not that molybdenum is such a particularly good material, but it has the advantage that it's very inert with respect to practically everything. If you look at the periodic table and you figure that the compound that we're talking about is a 1,3,6 type compound, almost everything you can think of on the periodic table will react with one of the components of copper, indium, or selenium. It turns out that molybdenum reacts only with selenium, and it reacts at a reasonably slow rate. Furthermore, it turns out that the formation of a little bit of molybdenum diselenide at the heterojunction is quite important to forming a good back contact. So molybdenum is actually a pretty good material. It's more resistive than we'd like, but it's a pretty good back contact material. The main active layer of the device is a chalcopyrite material. It's one of a variety of alloy compounds. We'll talk about that in a few minutes. The advantage of particularly the copper-based chalcogenides is that they have very high optical absorption, which means that at least theoretically you should be able to make a pretty good device with less than a half micron of material. People have made devices that thick, which work okay, but for better devices, pretty much uniformly, everybody needs between 1 and 2 microns of material. And the problem with that, of course, is that you're wasting a lot of expensive metal and source material and so forth. You have the potential for series resistance. And it's a continuing question as to why you need a micron to a micron and a half of material that is effectively inactive in the device. Presumably it's because you're establishing growth conditions, getting the grain sizes established, getting rid of some defects, and sort of optimizing the general structure of the crystals in the absorber material. We can hope that ultimately devices will be less than a micron thick when finally optimized, and that's something that requires research. The devices pretty much always use some sort of bandgap engineering, usually increasing the bandgap toward the rear of the device. That provides an effective electron mirror because these absorber materials are p-type. The minority carriers are electrons. You try to collect them to the front of the device, which means that you're trying to keep them out of the molybdenum back contact, and for that you usually increase the energy gap in the material, typically by adding gallium, but there are other ways to do that. Some of the devices have sulfur added at the front to push the valence band down and increase the energy gap at the front to try and keep the holes out of the front contact of the device. Normally, in a good device, you shouldn't have any recombination at the front. There are lots of issues to be resolved about the absorber material. The heterojunction partner is usually cadmium sulfide. That makes the best devices. It's not a particularly attractive material to use. We'd rather not have cadmium in the heterojunction partner material, but cadmium seems to dope the surface of the CIGS N-type, and that seems to be very important to the formation of a good device. So you'll see in the band edge diagram at the left, I've sketched the front of the Cigs material pretty much coming right down to the Fermi level in the conduction band, which means that you have effectively a homojunction of material in the absorber, with the cadmium sulfide being essentially electrically inactive as far as the device is concerned. And we also don't like the cadmium sulfide because the band gap is a little bit too small. We get a little bit of blue photon absorption in the cadmium sulfide. That loses us a few milliamps per square centimeter, and so there have been a number of efforts to increase the energy gap of the cadmium sulfide or to thin the material down. It's usually about 50 nanometers thick, and if you can get it down to about 20 nanometers, you don't observe that absorption in the cadmium sulfide. Alternatively, you can add oxygen, you can replace the cadmium with some zinc, you can add hydroxide or sulfur or something like that. Various options to the front contact window material to increase the energy gap. But cadmium sulfide has been pretty much typically the best material. And then the transparent conductor on the front, usually zinc oxide, can make it with indium tin oxide as well, but of course zinc oxide is less expensive. Looking for high conductivity and transparency, of course. Stability is somewhat of an issue, and appropriate work function, but there are a wide variety of materials that are used. Tin oxide is the main sort of exception that's not used as a front contact for these devices, the way that it is in cadmium telluride devices, for example. But mostly it's zinc oxide. So if we think about the substrate and interconnect that are used, typical substrate, soda lime glass is the main one. It's ideal protective material. It's really excellent in terms of taking care of hail damage, water penetration, and so forth. It's rigid, it's fragile, and it's heavy, which are unattractive properties. It's very inexpensive in general. On a scale of substrate materials, it's quite a reasonable cost for the basic material, but of course shipping is expensive. The other thing that's interesting about it is that it represents a reservoir for sodium. And we'll see that sodium moves around quite a bit in these materials. It's a benefit for those who have come out of the microelectronics industry like me. It's a little hard to wrap your head around that, but alkaline metals generally seem to improve the devices. Metal foils are another option. I show a couple of images here from Mia Soleil's devices. They can be made flexible. They're supplied as a web, which means that you can do an inline web coating tool, which is attractive in terms of sort of continuous processing and handling. But because the metal is conductive, it requires a different approach to interconnects that we'll talk about in a minute. You can also do polymers. They look very similar to the metal foil devices, and the main limitation with the polymer substrates is that they have a low maximum process temperature. And probably the more exciting result in that respect came out of Tiwari's group at EPFL, where they showed that they could do good high-quality Cigs devices at temperatures that are compatible with polymer substrates using potassium post-deposition treatments on the material. In terms of interconnects, there are two. One is the tab and string approach, similar to what's used in silicon, with some sort of a grid on the top. I've shown here screen printed, but you can use a wire interconnect that's attached by pressure contact or some such to the top of the device. And then those wires run across and connect the back of the next device over. The contact fingers do shadow the device somewhat, which can be a bit of a problem. And there are adhesion failures possible. The other alternative is the monolithic interconnect. And here what we're going to do is to lay down complete layers. It's what's used in the modules shown in the image at the top. So you pattern the back contact metal, so-called P1 scribe. You deposit the active layer and scribe that. That's the so-called P2 scribe. Then you lay down a transparent conductor over the top and scribe that using a so-called P3 scribe. And you can see that there are intrinsic shunts in the material, so the transparent conductor filling the P2 scribe is going to shunt from one device to the next. The active device material in the P1 scribe will shunt from one device to the next, and so forth. So there are intrinsic shunts in the device. The sketch that I show here, of course, is not to scale, so the shunts are not particularly much of a problem, but there are intrinsic shunts. Defects are common when you try to make these scribe lines. You can sometimes leave out little areas where it doesn't scribe completely, and that produces a shunt. And the scribe line itself, of course, is lost active area, because from one edge of the P1 scribe to the other edge of the P3 scribe, the device is inactive. And for some small area around that where the shunt current and so forth is dominating. So you lose some area on the scribe lines, and then the question is, how thin can you make the scribe lines? And you're trading off scribe area with number of cells. So you'd rather have a large number of cells to produce a high voltage, low current device to reduce series resistance losses. Materials that we're going to think about using, the alloy, the main alloy that's used in these devices has covered a wide range of materials. So on the group 1 site, you can use copper or silver. On the group 3 site, people have worked with aluminum, gallium, and indium. And on the group 6 site, sulfur and selenium. And you can do tellurium too, but that hasn't really been studied. Aluminum turns out to be a bit of a problem because it's so prone to oxidation. And most of the deposition processes don't use really high quality vacuum, so aluminum tends to be more of an issue. But it turns out that you can actually improve the device energy gap for energy gap, or output voltage for output voltage, by increasing the number of alloy constituents. So copper, silver, gallium, indium, sulfo, selenide, putting all of the elements together gives you the biggest increase in energy gap for an otherwise equivalent performance of device. But the best devices are copper, indium, gallium, selenide, possibly with a little sulfur thrown into the surface. I show you the ternary phase diagram below here, and the little tiny green area in the middle is the phase stability region for alpha copper indium diselenide. You can substitute gallium for indium. Pretty much all of these alloys are fully soluble, fully miscible with each other. And it turns out that you find quite a bit of additional solubility outside of what the phase diagram would suggest on the indium-rich side, moving over towards In2Se, indium selenide. So there's actually a fairly large stability range on the indium-rich side. These materials have a variety of energy gaps. When we substitute the cation, in general, we're moving the conduction band up and having very little effect on the valence band, which is handy. But if we want to move the valence band down, we generally substitute sulfur for selenium, and that primarily moves the valence band. And as I said, pretty much all of these alloys, to the extent that anybody has studied them, have found that the materials are miscible. There are no obvious miscibility gaps. And there's not a large amount of band gap bowing, which is consistent with the idea that you've got good miscibility in the materials. Unfortunately, indium and selenium are not terribly common, so people have looked at other materials. This is, by the way, the energy band diagram of the materials. So this shows that it's a direct gap material without a lot of other minima in the conduction band near the valence band maximum. You'll notice that there are a lot of curves in these plots because it's a complex band structure. It's a large unit cell, so the band structure is folded back on itself many times. And so we get a fairly high density of states consistent with the high optical absorption in the material. You'll also see that the copper d orbitals contribute significantly. So the reason that the energy gap is only about 1 electron volt in copper indium diselenide is that the copper d orbitals interact with the selenium p orbitals to push the selenium p orbitals up in energy. And that changes the energy gap. It reduces the energy gap significantly compared to, let's say, a zinc selenide or something equivalent in lattice constant and similar in chemistry. We also look at the kesterite, copper, zinc, tin, sulfoselenide materials. At least we have looked at this in the past. The crystal structure is shown at the right. It's a complex material, and it turns out to have a fairly large voltage deficit compared to copper indium diselenide. The data shown here from IBM, who was rather successful with copper, zinc, tin selenide for a while, but they never really solved the voltage deficit problems. Part of that is because there's so many ways that you can make andesite and point defects in the material, so you've got a lot of options for trouble there. Some of the interesting alternative materials are the ternary copper tin sulfide compounds that are shown here on the phase diagram, the ternary phase diagram between copper sulfide and tin sulfide. And those have not been explored a great deal, but they look like they are attractive for potential future studies. There's not a lot to say about them so far, though. If we think about how the absorber is made in these materials, there are several methods, the first of which is evaporation. This is how the record cells are generally made by a multi-source, multi-stage, complex evaporation process. Evaporation can be done fairly fast, but it's very difficult to scale up. And in general, to make good devices, it requires a heated substrate. This has been worked on for a while at Global Solar, and some other companies have used evaporation. Most successful one is probably either Global Solar or Solibro. They can be scaled up if you can make large evaporator tools. Probably a more popular method among manufacturers is salinization. You deposit the copper, indium, gallium precursor material typically by sputtering. It has the advantage that you can determine whether or not you got your precursor down correctly before you spend a lot of time on salinization. The precursor deposition can be done fairly fast, and it's not terribly sensitive to things like fast particle bombardment during sputtering or the exact details of the microstructure. And then you go into a salinization step. And there are a couple of problems with salinization. One is it's difficult with very large substrates to get uniformity in salinization. And the other is that naturally when you salinize the material, you add a bunch of volume to the copper indium diselenide, copper indium gallium selenide material that you produce, and that leads to stress in the film. And there are various methods that you can use, various tricks to control the composition profile of the material that you produce, and to control the stress to some extent. And this is the process used by Solar Frontier. And then there's sputtering. Sputtering has the advantage that it's relatively easy to scale up. It's relatively easy to control because the fluxes are linearly related to the sputtering current. And then you have to worry about things like fast particle damage. So anytime that you sputter a relatively heavy target like indium with a relatively light gas species like, for example, argon, you can get reflected neutrals bouncing off of the target and landing on the substrate. So you need to make sure that your process can handle that, and Mia Soleil has managed that. So let's turn now to looking at some of the products, and of course we need to start. No talk is complete without the NREL efficiency chart, and so I've expanded the part of the efficiency chart that relates to the materials we're talking about today. And the thing that's interesting about Cigs is that it's competitive in terms of record performances with all of the other thin film technologies, and in general it has managed to stay ahead of the cadmium telluride materials and the perovskites just barely, but Cigs has the most highest efficiency champion small cell device. So cadmium telluride in yellow following right behind Cigs, the perovskites making their startling excellent progress lately, and of course silicon in polycrystalline technology, the champion cells are just a little bit below the thin film technologies, and then crystalline silicon up above with higher efficiency devices. So there are a number of options, but in general the thin film technologies meet or exceed the performance of polysilicon, which is the inexpensive crystalline silicon technology. So the challenge is to make the chalcopyrite materials and devices for competitive levelized cost per kilowatt hour, and that means getting the efficiency of the modules up to this sort of champion cell performance, or at least pushing to or past the polysilicon technology in terms of module performance, and driving down the cost of manufacturing, which is a trick. I want to make a couple of comments here about the thin film technologies in terms of competing with the concept of the sort of third generation technologies that have been discussed. First generation, of course, is silicon. Second generation are cadmium telluride and Cigs. Third generation are some of the novel concepts that are being pursued. And this sort of famous representation here says this is an argument for why you'd need to go to third generation technologies. I just want to put the first and second generation technologies on this chart. And so the circles represent, the left-hand circles represent more or less the current technology performance. In the case of cadmium telluride and crystalline silicon, polycrystalline silicon, the prices are in the range of 50 to 70 cents a watt. Performances of products are in the 16 to 18% range, which puts them fairly firmly in the third generation cost line. And if you got the costs to the point that's projected and the efficiencies to the champion cell level, they would lie well to the left of the third generation technologies. So you should think about the thin film technologies, and indeed even crystalline silicon, as third generation concepts based on their performance. So we need to think about competitive success in photovoltaics for a couple of minutes, because it's really going to drive how we can manufacture these devices. So undoubtedly we have to have very fast processes. They have to be very inexpensive to create. They have to produce very efficient devices, and the devices have to be reliable over long term. So what do we mean by that? In terms of fast, we mean the slowest expensive step in the process has to be under 10 minutes, which means that an expensive tool has to pass the individual device through it in under 10 minutes, and preferably that has to be a very large device, and that just comes from amortizing the cost. For Cigs, that's a challenge, but there are examples. I'll show you one for very high rate processing. They have to be cheap. To be really competitive in the near future, you probably have to be in the range of 40 cents a watt, although that can be mitigated somewhat by higher processing rate, in which case your capital expense can be driven down, or by higher efficiency, which brings the levelized cost of electricity down. Cigs is making progress in this area. It hasn't really achieved the level that crystalline silicon and cadmium telluride have achieved to date in terms of manufacturing cost, but it's doing significantly better. You need over 18% efficient modules in order to be competitive in the long term. Cigs is very competitive in this regard. It's not quite at the level of 18%, but the modules are as efficient in general in product as cadmium telluride is, and very closely approaching the polycrystalline silicon module efficiencies, exceeding some of them, and driving the crystalline silicon people to need to use better and better production processes to increase their efficiencies too. And they need to be reliable. That means very low maintenance over 20 years or more, preferably 30 years, and Cigs is very competitive in that regard too. So if we think about some of the major manufacturers of Cigs, and I'm only going to consider three, although I will point out that three significant scale manufacturers is more than cadmium telluride really can boast, with First Solar being the only really major competitor in that area. Solar Frontier is certainly the leader. Their total shipments exceed 4 gigawatts over time. They're producing close to a gigawatt annually, and there's a photograph of one of their production processes. They're doing a lot of focus on automation and moving modules through their process lines very inexpensively. Their Champion submodule is better than 19% efficient, and that's something like a 100 square centimeter submodule. So it's not a very small module with excellent efficiency. They've got a number of projects worldwide in the sort of 100 megawatt scale, and as I said, they're shipping close to a gigawatt annually, mostly focused in Japan, Europe, and North America, and to some extent other places in Asia. They sputter the metal precursors and salinize after deposition, so they can do their sputtering process, their metal precursors, at a very high rate. Salinization can be done either in inline furnaces or in batches, depending on how you can get the uniformity of the salinization process optimized. And then they do chemical bath deposited cadmium sulfide, to the best of my knowledge, and of course I don't know in detail what they do, but my understanding is that they use chemical bath deposited cadmium sulfide. Solibro is a Swedish company, now owned by a Chinese company. They use a monolithically integrated glass encapsulated product. Looks very nice as far as I'm concerned, very uniform black color. It's a co-evaporation based process that they use, so they've succeeded in scaling up co-evaporation to quite large substrates, and they get beautiful uniformity. They're really nice uniform looking performances. They have generally done chemical bath deposited cadmium sulfide. They may do other things. I'm not sure what they're using exactly for a heterojunction partner, because of course none of these companies talk about it very much. They have a 17.9% efficient Champion full-scale module. So modules that are close to a square meter, they've achieved a 17.9% efficient module, and that's quite an accomplishment in a monolithically integrated module, because every part of the module has to operate very well to achieve that sort of efficiency. They are selling their products, for example, as residential kits through IKEA, and So they're primarily targeting smaller arrays on residential rooftops and so forth. And they have about 145 megawatt production capacity currently. Mia Soleil, which is another part of Hanergy, so Celebro is part of Hanergy, so is Mia Soleil. And they are making both flexible and rigid products. They work on stainless steel foils, and they have high record module performances comparable to the Celebro records. They're mini modules. They don't indicate sort of a mini module performance, but their 1 square centimeter performance is about 19%. Their rigid 1 square meter performance is over 17%, and their 0.3 of a square meter flexible product is 17.5% champion. So their manufactured modules can exceed 17%. One of the things about their technology is that they make individual cells, and because they make them on a stainless steel foil, they're tab and string interconnected, and that means that to some extent they can match their individual cell performances to get high performance modules by tailoring their cells to work together with each other very well. They have about 170 megawatt manufacturing capacity currently, with an average product efficiency exceeding 16%. So they make a very good product, getting to be very competitive with the polycrystalline silicon and cadmium telluride products. They are about 50 minutes bare foil to finished device. So it's a stainless steel foil that runs through their whole process tool and out the other side in about 50 minutes, which is a good rate of deposition. That means that they can process bare foil to completed modules in quite rapid timescales. So that's very competitive. In particular, they can deposit 1.5 microns of Cigs in about 5 minutes. So we said that that was necessary to be competitive, and in fact they do that. It's an all-inline vacuum process, so that's attractive. And they have about 80 megawatts in the field. One of the things that's attractive about it is that because they make individual stainless steel cells, they can make tailored products for individual customers if they need to. So now let's turn for a few minutes to technical challenges that remain. Multi-junctions are one of the sort of holy grails of Cigs technology. We'd really like to be able to do this. What we lack is high voltage, wide energy gap materials that work. You can see from the chart on the left, thanks to Tim Anderson and others, that the efficiency of the devices, the champion cells, increase with energy gap of the material, but then the voltage ceases to improve and the overall efficiency of the device drops as the energy gap grows, because you lose current without really gaining any voltage. Product efficiencies need to approach champion cells more, so typical products are moving into the 16% efficient range, but that still lags well behind the 22% efficient champion cells, and it lags behind some of the product in multicrystalline silicon. Although multicrystalline silicon isn't that far ahead, this chart is a little out of date. We need to understand and control metastabilities. So for example, there's potential-induced and light-induced metastability in the devices, and we need to understand that. We need to understand the voltage deficit, which isn't as bad as it could be, but it still is one of the major losses in the device. And we need to improve reliability. And here there's a chart provided by NREL that shows some of the major typical failure mechanisms for thin film devices. You typically have infant failures early on, and then you have occasional failures during the midlife of the material, and eventually the device wears out, and you hope that that occurs after the warranty. So multi-junctions, certainly what we'd like to do, we have the advantage that there are a tremendous number of materials that we could choose from. Copper-indium diselenide itself provides a very good bottom cell because that's a 1 eV gap material, and we can make, for a 1 eV gap material, we can make quite nice devices, but they're too low on energy gap for normal operation. But there are plenty of alloy options for wider gap materials. The trouble is that most of those wider gap materials, like copper gallium diselenide, for example, or CGS, don't work very well. So as we increase the energy gap, pretty much uniformly all of these materials fail. We can combine them with other materials like cadmium telluride or perovskites, but in general, those materials have too small an energy gap for a 2-junction tandem, and so we need other materials that we could go even wider gap for a true ternary 3-junction device. In general, the Cigs devices have the wrong energy gap to combine effectively with silicon. It's pretty much the same energy gap as Cigs, so that doesn't really work. And so we are looking at complex alloys, especially sulfides. Of course, to make a multi-junction device, we'd need to think ultimately about tunnel junctions and how to process one device without affecting the other, and people are working on that. There are a certain number of limitations to Cigs resulting from defects. Admittance spectroscopy, where you measure the capacitance of the material as a function of temperature. Here I show the derivative of an admittance spectrum taken at a range of frequencies. And what you're looking at is release of trapped carriers from defect states. In this case, there's a 240 millielectron volt hole trap, and there appears to be a 600 millivolt hole trap as well that shows up at the higher temperatures in the material. So there are a couple of trap states that you can find. The 240 millivolt deep hole trap is pretty much observed ubiquitously in all of these devices. The one here has a concentration of about 4 times 10 to the 15 per cubic centimeter, which probably not coincidentally is about equal to the acceptor concentration in the material. So it may be the same defect giving rise to the primary acceptor in the material that also gives rise to the 240 millivolt hole state. Transient photocapacitance and deep-level optical spectroscopy have been used to observe a trap state typically found around 0.98 eV. There's sometimes a second trap state observed around 0.8 eV, but certainly both techniques show pretty clearly a state at about 0.98 eV in the material. It correlates with performance, and it's reduced by alkaline metal content. The mid-gap state, the 600 millivolt state found by admittance spectroscopy, is also observed by deep-level optical spectroscopy. The thing about the 980 millivolt trap, the one that's around the conduction band edge in copper-indium diselenide, is that it stays at the same energy with respect to the valence band. So as you increase the band gap by adding gallium to the material, that trap state moves more and more into the middle of the gap, and eventually probably is what limits the copper gallium diselenide devices from working. We can also observe defects through a variety of optical techniques, for example, photoluminescence. If you look at the photoluminescence intensity as a function of temperature, at least in some cases, we've observed a quenching behavior that's consistent with a band tail behavior, similar to what's observed in amorphous silicon. But you can observe band tails a lot more easily with scanning tunneling microscopy, and I show some results here for what's called spectroscopic scanning tunneling microscopy. You put the probe tip over a particular location on the surface, and scanning tunneling microscopy gives you atomic resolution. And then if you sweep the voltage of the tip, you can measure effectively a current voltage relationship, and that gives you effectively the band edge density of states. And what you see is that copper-indium diselenide has a really large range of fluctuations in the band edges, and both band edges are moving all over the place. Silverium diselenide has much less fluctuation in the band edges, and in particular the conduction band edge is quite uniform and shows relatively little fluctuation. And it's these band edge fluctuations that seem to correlate with performance of the device. So both the sort of known defects that are in the gap, the 240 millivolt state, the 600 millivolt state, and the approximately 1 electron volt state, all correlate with device performance. Band edge fluctuations also correlate with device performance. Alkaline metals are sort of an interesting case for these materials. They can be a blessing and they can be a curse. So they reduce the process temperature. They improve the molybdenum back contact by promoting salinization of the molybdenum. They improve the open circuit voltage by reducing recombination. And post-deposition potassium fluoride treatment has a tremendous advantage in improving the device. The materials appear to act through grain boundaries, so we find the alkaline metals segregated in the grain boundaries and not particularly found in the grains. So whatever they're doing, they're acting through the grain boundaries. The problem with them is that they move around at room temperature, and in fact there's data that I'll show you in a minute that shows that the materials actually electromigrate during operation of the device. Too much sodium is a problem. That's correlated with the electromigration problem, and the electrochemistry of the materials, the coming and going of the alkaline metals is complex. These movements of the sodium may be responsible for module instabilities. So here's some data from Laurel Mansfield at NREL, where she's measured the effect on devices by applying a potential to the encapsulation. And so if you think of a glass encapsulated device, the glass is a thick layer. It's up to 4 millimeters thick, so it's not a thin material. But if you ground the front or back surfaces and apply a high voltage to the interior of the device, you can drive sodium in or out of the device. And just to sort of summarize Laurel's results, if you have a bias between the front side of the device, in other words, the transparent conductor or the zinc oxide side, and the exterior of the device, plus and minus 1,000 volt bias to the device relative to that exterior surface, you don't have any particular effect. But if you apply a bias between the back surface of the encapsulation and the device, never mind the fact that the glass is apparently electrically insulating, you can drive impurities around, and apparently the problem is associated with driving sodium into the device based on a negative bias to the device relative to an outside contact. And my Cigs array came with very specific instructions as to which side of the device to ground so that the exterior surface of the package would be negative relative to the device as much as possible. So this is quite important in maintaining operation of the device. One of our problems, as I mentioned before, is that champion cells perform better than modules. Champion cells, of course, are not average cells. They're the best cell that anybody ever measures in a given shop. Local defects have a large impact on the performance of modules, as I show on the right here. And in particular, if you're making modules, manufacturing compromises are inevitable. You pretty much have to move away from how you make a champion cell in order to make your process manufacturable, which is why the champion cells that I mentioned from Solar Frontier, Solibro, and Mia Soleil being approximately 19% is important, because those are manufacturable technologies. We design modules in general to maintain specification and not to have one good module for champion performance. So again, compromises in the performance. And local defects are hard to avoid over large areas, especially in monolithically integrated modules. Monolithic integration has intrinsic and extrinsic problems, as I mentioned before, but it is very nice for manufacturing. And in tab and string technologies, the individual cells can differ. And so it's always a question of whether you can match them well or not. Reliability is important. Cigs is intrinsically a very reliable product. Typical degradation rates, as shown in the plot below from Dirk Jordan at NREL, are typically about 0.5% per year. And in fact, you can see from the plot on the left that Cigs devices can actually show an improvement initially in the first few days of operation. They can get better before the performance starts to degrade over time. One of the things that certainly happens is that shadowing can have a big negative impact. I'll show you some data on that in a minute. And of course, NREL has accumulated a large amount of data on these devices if you want more details. The damage from partial shading is shown here, data from Tim Silverman at NREL, and they've looked at shading of the modules and found that any kind of shadowing that you put on the module produces permanent damage. Although the modules that I have, the array that I have, has severe shadowing problems, especially in the wintertime, and it still operates reasonably well. So that certainly hasn't killed the array at all. But it can produce a lot of local defects. If you look on the plot on the right, you'll see that there are quite a number of local defect points that show up in electroluminescence. The module tested here lost about 17% in max power due to shading-induced shunting of the module. So you can see from top to bottom, the shunts are showing up as the little black dots throughout the material. One more topic, and that is elemental abundance, because that's why we looked at other materials. Indium and selenium are relatively rare. They're similar to silver in abundance. Fortunately, they're much more common than tellurium, but there's enough of them available to sustain a pretty large industry. Nonetheless, there are problems. Indium is used in a lot of high-value products like the display you're probably watching this talk on. They're used in all sorts of transparent conductors, and so that's a problem. This is why copper zinc tin sulfide was tried, but it has too many native defects. And so that's why people are looking at these ternary copper tin sulfide compounds. So there's good potential there. So just to wrap up, in terms of conclusions, chalcopyrite solar cells are very competitive for reliability and efficiency. We need processes to be faster, or at least with less capital expense, or lower amortized cost per watt over time. There are a lot of science questions remaining. I've only mentioned a few of them. Multi-junctions are possible from related materials with possible large benefits, but there are huge technical challenges in terms of figuring out how to do that. We need to increase deployment to increase trust in technology recognition, but the technology is still very competitive. So thank you very much for listening to me, and if there is time for questions, I'll be happy to take them.
Thank you, Dr. Rockett. Anyone has questions, they can tell them. Anyone have questions?
And I can't see the chat window, so if any questions show up there, I'll need them read to me.
Okay, well, I guess it sounds like you probably answered everyone's questions during the talk. So thank you, Dr. Rockett, for taking the time to speak with us and give this update on the chalcopyrite.
Even my snarky comments about third-generation technologies haven't caused any questions.
So if anyone would like to participate or tune in the future, please keep an eye on our website, nextgentv.org. Thank you again, Dr. Rockett. Great. Thanks again, everyone.